Hey guys, Mr. Smith here, and in this video lesson, we are going to derive an equation that quantifies the magnetic force on a conductor. So let's get started. So our starting point off today is we're going to build on the fact, so we already know that an individual charged particle that's moving in some magnetic field, and it has to be moving, is going to experience a magnetic force. So if you imagine a whole bunch of particles moving through charged particles moving through a wire, they're going to experience a force too. But because the particles, those charged particles, are contained within the wire, like they can't fly out of the wire of the insulation, what happens is the wire itself experiences a force, and it might not be the material that the wire is made of, like the plastic coating or whatever's on the outside of it, but it's because the particles inside experience a force and they can't leave the wire experiences a force. So that's kind of our starting point. The diagram we have here is just illustrating this idea that now we're just moving beyond a single charge and we're talking about a current. The symbol we use for current is I. I believe I mentioned this several other times, but something you guys learned in your grade 11 course is that the direction of current is actually defined to be the flow of positive charge. So we understand that it's electrons and free electrons that are moving inside a wire that provide the current. But in our diagram here, the current is flowing, the direction of positive charge is away from this positive towards the negative. The actual electrons would be going the other way. I'll just say electron flow. So just something to keep in mind. And we've got tiny little right-hand rules that you can see on these diagrams. And if you just want to get further practice with your right-hand rule, in this question, we have the magnetic field kind of pointing right on our page, and the current is kind of pointing into the page, so towards the screen, so like this. So that's the way I'm looking at it, and my palm is going down. So, and from my perspective, a positive charge would experience a force down, and so if the current was reversed, it would reverse the direction that the force is. So let's talk about a formula for the force on a conductor, because we know the force on a charge, but a conductor has lots of moving charges through it. So it depends on a few things. So our starting point is going to be we're going to say N is the number of all the charges in a wire or a conductor of length L with a certain current I. So off to the side here, I'm going to do a couple things. So if you recall, current is basically charge per unit of time flowing through a specific point in a wire. So if we think about over a certain amount of time, how much charge flows through the wire, it would look like this. We have N times Q divided by delta T. And again, it's because current is coulombs per second. And this is the number of, that's the current moving through the wire. So again, current is just charge divided by unit of time. So every second we have N times Q kind of charges flowing through the wire. So you have an expression for I, and we can rearrange that. So Q would then equal I times delta T divided by N. And we're also going to make use of the fact that speed equals distance over time. And according to our setup, so the distance that those charges travel in that time through the wire, we called L. It's the length of the wire. So we'll make use of that. So we have a bunch of, and these may be electrons, that's fine. So they have the current is like the amount of charge going through the wire in a certain amount of time. We rearrange for the charge and then use the fact that speed distance over time to get an expression for the speed in terms of L over delta, the length of the wire and time. So let's make use of that. To the left. Now we're going to make use of our force on a moving charge. So we had Fm equals Q VB sine theta. And now we want to know, though, the force on like the whole wire. So we're going to take our expression for Q and plug it in. Delta T over N. We're going to take our expression for V and plug it in. L over delta T, B sine theta. And so notice the delta T's divide out. And this is the force on one particle. The force on the whole wire so I'll just simplify that. So we get I times L times B sine theta over N. And so for the whole wire, if you multiply that by N, the number of charges in there, this is the whole wire. You get the force on a, oh, don't zoom. What are you doing? Zoom out. Oh dear, what happened? Okay, I right-clicked, that got out of it. The force on our conductor, ILB sine theta. So that's pretty cool. So it's very structurally similar to the force on a moving charge. So it depends on the current, the length of the wire, the magnetic field strength, and sine theta. And so now that we've derived that formula for the force on a wire or a conductor, we can just start using it. Now I actually teased this earlier, but now we actually get a better understanding of what a Tesla is. So if you take that equation and rearrange it for B, you get this. B is equal to Fm over I L sine theta. And so this gives us a way to interpret the Tesla. So the Tesla is the magnetic field strength present when a conductor of length 1 meter and a current of 1 amp experiences a net force of 1 Newton. So that's a little easier to visualize. So if I have a 1 meter long wire and I run a current of 1 amp through that, when my wire is experiencing a net force of 1 Newton, I know that I have that required field strength of 1 Tesla. So the right-hand rule for conductors, it still holds. It's not really a new right-hand rule. If you want to think of it as another one, that's fine. It's kind of the same right-hand rule, but it's just for conductors. So remember, we take our fingers, we place them in the direction of the magnetic field. That doesn't change. This time our thumb is in the direction of the current, which is basically the same as before, because the current is the direction of positive charge. So it represents the velocity, still kind of the same thing. All these charges are moving with velocity v in that direction. And the direction of the force comes out of our hand. So remember the definition, remember the concept I explained earlier about thinking about an arrow and whether it's going into our page and out of our page. Think of the right-hand rule here. So we've got our fingers pointing kind of to the left and up on our screen, with the direction of current pointing up and right on our screen. Which way is the palm facing? The palm's facing towards us. So the force on this wire would be out of the page, pointing straight at us. And that's because if you think of an arrow, it's like we're looking at the arrowhead coming out of the page. So the right-hand rule, it still holds for conductors. It's the same right-hand rule. But I remember that current is the direction of positive charge. So didn't have anything to add to that. So let's do an example. And just look at just as what we haven't really discussed is kind of varying the angle a little bit. So here we have a straight conductor, 10 centimeters long, with a certain current, and it moves through a uniform 0.6 Tesla magnetic field. So we're going to find the force in the conductor when the angle between the current and the magnetic field is 90, 45 degrees, and 0 degrees. So I'm going to actually just draw a little illustration down below. So I'm going to draw my best kind of drawing here of Faraday's experiment that he had in the mercury. I don't think that'll be too bad. So if you can imagine, my solid line here is a wire that has some current flowing through it. And the dashed line here just represents it's kind of a symmetrical counterpart, and that wire would just kind of spin around. We have this magnet is going to be exerting some, or is going to be creating some magnetic field. And the current in the wire, so that's B. And the current in the wire, it doesn't really matter which way I have it flowing. Say the current's going that way. And so when the wire is perpendicular to the field, so that's when we're going to have our biggest magnitude of force. And that's the situation that's happening in part A. We've got 90 degrees. In part B is saying, imagine the wire, instead of like being vertical, was like that. So the current in B kind of flowing like that. And so it would still experience a force, but maybe not so much. And then part C is saying that the wire is like perfectly horizontal to it. So let's just do these sample calculations. The results really shouldn't surprise you at all. Just basically, we're just getting used to the formula here. So Fm, ILB sine theta. And we're simply just given all these things, right? So 15 amps, 10 centimeters. So make sure we're working in standard units. So that's 0.1 meters, 0.6 Teslas. And then part A is saying the angle is 90. So we know that sine 90 is 1. That gives us our maximum possible force, 15 times 0.1 times 0.6. So we get about 0.9 newtons. For part B, so if the wire was at like kind of an angle to that magnetic field, we would have the same calculation. It would be 15 times 0.1 times 0.6 times the sine of 45. So that's going to be obviously less. About 0.63 newtons. And finally, if it's horizontal and the angle is 0, 15 times 0.1 times 0.6, but the sine of 0 is 0, and actually that conductor would not experience a force. So just a quick example, playing with the formula. That's about all that you guys are going to do with the force in a conductor, is just be able to use the formula and solve given 4 of the 5 things, find the 5th one. You guys should know that it's a maximum, just like with a moving charge, when the angle between the current and the electric field is 90. But you guys also need to be able to apply the right-hand rule for conductors as well as moving charges. But it's the same right-hand rule, but you guys just have to remember that the direction of current is the direction of positive charge. So if a current is moving to the right, that actually means that the positive charge is moving right. The electrons themselves are moving left. So just something to keep in mind. Just to finish things off, this idea of a magnetic field creating a magnetic field exerting a force on the current, but also a current generate a moving charge generating a magnetic field, is the idea behind the motor principle. And it explains how motors and generators work. And depending on who you had in your grade 11 course, maybe you spent a lot of time talking about this, or maybe you didn't get to spend a lot of time at all. But in general, what motors do, motors convert electrical energy into work. So a motor might take electrical energy, so flow a current through a wire, and it generates a magnetic field around it. And then if you put some small magnet in that magnetic field, it's going to get dragged around. And if you're dragging this magnet around, it has the capacity to do physical work. So that's kind of the idea behind motors. Generators go backwards. They convert mechanical work into electrical energy. So in the same scenario, if you were to spin this magnet around and around and around and around this wire, you'd actually generate a current in the wire. And that's why all the things we have for generating power are all kind of like turbine based. Like think about a big wind turbine, those big arms in the sky just going round and round. We've all seen them. So as they're turning, they're just dragging really big magnets around and around some coiled wire and generating a current in that wire. It'd be a lot of fun to dive into electricity and magnetism a lot more, but just the nature of the course, got lots to do. And this is kind of where we'll wrap up our discussion with magnetic forces. We've kind of done our field theory. So to be clear, what you guys should be able to do with magnetic forces, you should be able to use the equation for the force on a moving charge and the equation for force on a conductor and be able to apply the right-hand rule in either case. You should also be able to kind of understand, maybe not recreate, but understand our derivation and the work we did looking at charge to mass ratios and mass spectrometers and how the mass of an electron was found out. In our next unit, we're going to turn our attention to the universe on a big scale and on a small scale. So we're going to look at the matter-energy interface of the universe. We're going to talk about special relativity, so kind of that grand scale. And also on a small scale, we're going to talk about nuclear physics, which essentially we'll just be looking at various applications of Einstein's famous equation E equals mc squared, talking about nuclear fission, nuclear fusion, and a little bit of radioactive decay. So it should be a lot of fun. I really enjoy teaching that. I've practically been enjoying teaching all of it, but especially I love talking about relativity. All right, so I'm rambling. Let's end it there, guys. Hope you guys are staying well. Have a great day, and we'll see you soon.